and for IB not there. What is there? The current for the phase C, which is IC, 10 at an angle 120 degree negative ampere. So what we are asked to do again, we are again asked to find out the sequence components of currents and also the neutral current, which we did not consider in the two previous tutorials that we did. Now how we do it is the same formula that we are going to use. Like if I go back, I can even copy and paste these three formula that we will need here, and for you you'll say it's easy. For me, I'm just copying and pasting. You'll have to type it. Yeah, you have to. I'm sorry, but I will give you time for you to calculate, and we will again verify the answers, what is happening with each of those answers. Zero sequence current, IA0, then its formula is 1/3 IA plus IB plus IC, and positive sequence current formula remains the same, IA1, which is equal to 1/3 times IA plus AIB plus A squared IC. Negative sequence current IA2 is again 1/3 times IA plus A squared IB plus AIC. So we will have to calculate these values, and we'll observe and discuss why we are getting such results for these three sequence components of currents. So you start doing your calculation, and when you get the answer, please let me know. You can tell me keeping your microphone on, or you can type your answer on the chat facility as well. I'm recording this session, so don't say something, or yeah, I'm just letting you know that I'm recording this session. Anyone who has got the answer?
So
Yes.
is IA0 3.33 at an angle of minus 60 degrees?
You're saying 3.33 at an angle minus 60 degree. Let's see what others are getting. 3.33 angle of minus 60 degree.
Yes.
Okay. IA0. But I got plus 60 degree. I don't know, maybe my calculation was wrong, so I need to hear it from anyone. If you got 60 degree plus positive angle, not negative.
So I'll double check it.
Yes, please. All others are quiet. You should tell us the answer. You're just not supposed to sit down there and waiting for others. Okay, waiting for others to tell what is the value of IB. Read the question paper. Question paper is telling that phase B of supply is found open. So you have studied second year, third year. Let it go for the first year. So when a supply line is open, what happens with the current? Think about it. You must know that if the line is open, your power supply line is open, what happens to the current? What can happen to the current? Yes, Singo, you got it right now. Thank you very much. You think you always, I mentioned to you sometime, I'm sure, that you to thinking all the time. Are you
For IA1, I'm getting a 3.33 and the positive 60 angle. I'm not sure if it's correct.
IA1?
IA1, I'm getting 3.33 and the angle of 60 degrees. But let me double check if I.
IA1 or IA0? We are the first one is IA0. IA1 is the second one. IA2 is the third one. So are you sure that you mentioning 3.33 at 60 degree positive IA1?
Let me double check, but I thought I was calculating for IA1. Let me double check if my
Okay.
calculations are
The formula are on the screen. If you look at the screen, you will get the formula there.
So the angle for IC is minus 120 degrees, am I right?
Yes.
I'm still getting negative.
Okay, maybe my calculation was wrong. Okay, so 3.33 at an angle 60 degree positive. So let's go to, I'll check my calculation later on. So let's go to.
No, sir.
No, sir, we got minus.
Sir, for IA0, it's negative 60.
Yeah, that's what I have had.
Yeah, for
Yeah, that's what we got, sir.
You got it now, right? 3.33 negative 60 degree.
But for IA1, it's I think Luto. Yeah.
60 for IA1.
IA1 is
same magnitude, but the phase angle is positive 60.
Same. IA1 is 3.33 as well.
Yes, I got 3.33.
Okay, let's hear it from others. Luto has written here that 6.66. And the angle?
No, sir, it's 3.33 at an angle of. Yeah. I think that's what Luto said. I'm not sure.
Luto on the chat, Luto is saying that it's 6.66 IA1.
It's 3.33, sir.
I got 3.33 at an angle of positive 60 degrees.
IA1.
Yes, I also got that too.
Yes, sir.
Okay, let's verify it. The formula for IA1 is 1/3 times. Maybe I should put that 1/3. It's not mathematically right. I should put them in the bracket. Otherwise, it's like 1 over all the way. It's wrong. If I put 1/3, then IA is 10 at an angle 0 degree, right? So that's 10. And then IB is 0. That becomes 0. And then IC is 10. And then you have minus 120 degree. So squared 3 times. If you now calculate it, you're getting 3.33. Are you sure? You said how many degrees? Positive 60.
Yes, sir. I'm double checking it now, sir.
Okay. For a squared, there will be 240 degrees, and it's already a minus 120, so it will be 120. Am I right?
So the value of A is 1 at an angle of 120, am I correct? Just the operator A.
A is 1 at an angle 120 degree. That's correct. 1 A is equal to 1 at 120 degree. So 1 at 120 degree times 10, it has to be squared. So it will become 1 and 240 degree, and then you multiply it with that 10 at an angle minus 120. So that should give us 10 at an angle 120.
So for the negative sequence currents, I'm getting 6.66 or 6.67 if you round it off.
That's fine. At an angle
0.
0 degree. Everyone getting that? I think now we got all the three values. Now can you see what has happened? Previous cases we were getting only one value as having the magnitude. Other two were found to be 0. But in this case, all the three components are present. That's why we cannot ignore. We cannot just work with only one value, voltage or current. In this case, the example is talking about the current. Three sequence components currents are present. So for this type of analysis, we will have to, this is a real example of asymmetrical or unbalanced system. The system is unbalanced because of the phase B supply line found to be open. All the three sequence components are present. Their magnitudes are different, angles different from each other. They are not separated from each other by 120 degree anymore. So that's the understanding of this tutorial. And now the next part is to calculate the neutral current. IN is the sum of all the three phase currents, IA plus IB plus IC.
So for that, it'll be 10 at an angle of minus 60 degrees.
10 at an angle minus 60. And interestingly, we should at an angle minus 60. And it should be interesting to find that we derived that in theory, but we probably have forgotten. We can find again, or through our observation merely, if we forgot it completely, this neutral current is actually 3 times of IA0. Can you see that?
Yes, sir.
Can we see that it's going to happen all the cases when we have a star connection, neutral grounded solidly. This is a very good observation that if we have forgotten from our theories, we can verify it. 3.33 we rounded off there, and if we did not, if we kept it as 1/3, then we get perfectly 10.000. Everyone okay with this?
Yes, sir.
Okay, that's good. We can go to the, I will give you others 30 seconds to write down this last line, neutral current, and that relationship between the neutral current and the zero sequence current, which is one of the most important aspects that we find, is a feature that we find and utilize So we need to now go to the next one. Next one is about a delta connection. What it says that with line C of a three-phase system open, the current flowing in the line A of a delta connected load is 10 ampere. They're not talking about the angle. Find out the sequence components of currents. So can you see now when we coming to this one, we even reducing in the first two examples, everything were given, all the voltages, VA, VB, VC, the magnitude, phase angle, phase sequence. The same thing we did for the second tutorial, currents were given, phase sequence was told, and the angles were given as well. Now in the third one, we considered a star connection. The current for phase B was not given, but it was mentioned that the supply line B was found open. Now when we come to the delta, we find that we also have a case where the line C is open and current flowing through the line A is given, whereas they don't talk about anything else, but they are still asking us to find out the sequence components of currents. So if I draw it, I have it. Let me just copy and paste the diagram so that you can see what is happening. So it will look like this if I draw it like, I have to make it big. Okay, please remind me about the figure sizes. When I was marking, and I forgot to mention that in the feedback list that I gave you, the figure sizes were ridiculously large. Some figures were taking almost the whole page. So, okay, let me take this opportunity just now. When you put a figure on your report, you must not sorry, I just was closing the door. You must not make the size such that it becomes too small or too large. It's bad. I won't show you your report on the screen so that others will see what you have done, but let me show you what I have. For example, let me find it out. How a figure should be ideally. You should have seen them from the journal papers, but let me show it here so that can you see the size of a figure and the clarity, the use of colors, legends were not there in many cases as well, how prominent the texts on the axis, on the X level, Y level, the legends, the color, the line marker, the colors that are used are also very important. So this is the size that should be there. But what I found in the report, let me make it big enough so that you can see figures were like this size. Sometimes it was just like that. And I couldn't see what the figure caption is. So large. And also another point I forgot to mention is that I found there was no proper style in the figure caption. I wrote it in general though, that the figure captions were wrong. I did not find a style in the figure caption, and then I found that there is no semicolon or anything after the figure number. Not only that, the first letter first word was not capitalized. This has to be, you cannot just have a caption like this. This is wrong. Starting with the lowercase letter, it is wrong. It's wrong. It has to be capital T. But sometimes when we have many graphs, what we do, we don't want to just show people that I have written a very long report. So what we do, we put two graphs in two columns. Normally we write single column report. So when we have single column report, this is what we do. Figure size so that everything is clear. It can still be reduced a little. This is also fine. But when we have many graphs in one report, we can put them into columns. That reduces the length of the report. And if you to put them, they should be coming like that. And the thing that I was telling you, that captions cannot be the same. So what I did, times graphs for simulation results, for calculated values. I'm not using the same caption here. I'm saying IEEE characteristics simulated, IEEE characteristics calculated. They are caption certified. So that's what I wanted to show you. Let's go back. So this is the diagram. It's showing a delta connection. The phase line current, not phase. The line current for the delta is given, and that is 10 ampere. They said line C is open, so that line C is shown as open. The line current will be 0, like Sengo asked in the previous case. Now IB we don't know. So what we should do, we first write that IA is given 10. We assume the angle to be 0 degree. Right. Then IB, we don't know. Then IC is 0. Now, from a delta connection, we should know that IA plus IB plus IC is equal to 0. So from this equation, actually we can find out what is the value of IB. You find out that sum of all the line currents should be equal to 0. So can you find out the value of IB, and then we can proceed to the next steps. Who has the value? It's very simple. Should not take more than 20 seconds, 15 seconds. Yes, 10 at an angle 180 degree. It's correct. I need to just hear it from one or two of you.
I got the same, sir.
Yeah, that's good. Thank you very much. Yeah.
When dealing with these connections, we're dealing with the line currents and not the phase currents.
Yeah, line. That's why I drew this diagram that you see there, so that we don't get confused. Now we can go to calculate the sequence components of currents. I'm just changing them to capital letters. Minus 10, IA 0. Oh, you're saying minus 10, 180 degrees. Single. It's 10, 180 degrees. If it is minus 10, then it is plus 180 degrees. Yes, minus 10 per plus 180 degree. And what I wrote there? No, you're saying minus 10, 180 degree. No, that's not right. If it is minus 10, then it's 0 degree. If it is minus 10, then it's 0 degree. If it is 10, then it is minus 180 degree. Because you're going at the opposite direction. It's the phasor, you're reversing its direction. If you remember, these were very in the very beginning of phasor. Like if I draw one here, let me say I can draw. This is my phasor. Yeah, it has an arrow. So if I say that this is A, sorry, this is A, and obviously it's the way I drew it, it's parallel to x-axis. It will be at 0 degree. Now I don't want to draw it like this. I just want to. So if I drew it like this, the same phasor, I can do that. And when I come to this, then it will be minus 180 degree or plus 180 degree, or you need to put minus. You can think about that. So the answer was for IA 0.
Third 0.
0. That's correct. And then the positive sequence, when you get it, let me know.
So I got 5.77 at an angle of minus 30 degrees.
Yes, that is also correct. 5.77 minus 30 degree. Oh, sorry. And then we'll have to find out IA 2.
So for that I got 5.77, but this time the angle is positive 30
degree. That's correct. So we got all the three values. I'm giving you 1 minute to write this down, or if you have answer to verify. 1 minute. I'll give not 30 seconds, 1 minute to write down the answers and verifying it for some of you. Then we'll extend this to something else which we did not do for other tutorials. But that should be easy. We covered that part in our theories. So who has got the answer for IA1? 5.77 ampere at an angle minus 30 degree, and negative sequence current IA2, 5.77 ampere again, but the angle is now positive 30 degree. I guess you got it. Otherwise you can take it from this one. Now if you have noticed, for all these 4 tutorial from yesterday up until now, we calculated the IA0, IA1, IA2, or VA0, VA1 and VA2. We never worried about what is happening about IB0, IB1, IB2, or even IC0, IC1, IC2. We never talked about that. So I want to do that part here as well. So what we want to do, we need to know what is, let me just extend this text box, IB0. I want to know what is the value of IB0. What do you think will be IB0? Anyone?
It'd be 0, sir. It would be 0.
It will be 0, but why? Because we know that zero sequence currents are same, equal in magnitude. IB0, IC0 should be equal to IA0, because we have found IA0 is equal to 0. That's why we can say IB0 will be equal to 0. Therefore IC0, we find it in the same equation, that IC0 will also be equal to 0. Is that clear to everyone? So we don't stop only calculating the IA values. We also need to know the IB sequence component currents, IC sequence component, IA0, IB0, IC0, IA1, IB1, IC1. So now I need to know what is going to be the value of IB1. And of course, I will also need to know the value of IB2. Of course, again, I will need to know IC1 and IC2 as well. So if you can remember how we can calculate IB1, IB2, IC1, IC2, you tell me, otherwise we can go back to somewhere. It's easy, we don't have to memorize. I explained it in the theoretical part that we don't have to memorize it, we can still find it. What should be the formula or the expression for IB1, IB2, IC1 and IC2? Can anyone remember? You don't need to go and open any PDF slides from the website. Don't do that. Wait, if you can remember, it's okay. If you cannot remember, we can find it out again. It's easy. Anyone can give me a hint on this? Okay, how do we do it? IB1, right? B1, 1 means positive sequence, that we know. We don't have to memorize. 1 means positive sequence, 2 means negative sequence. So if I don't now remember what is the expression for IB1, how do I do it? I just go and draw the phasor diagram of positive sequence. Where is the shapes? So I'm drawing it. Let me just try rotate it. So this is IA, and let me put another one for IB. Let's say this is IB, and let me take another one for IC. It's not to the scale, don't worry about that. We're just trying to get the expression. So this is okay, I have to write down those, copy, paste, this things. help. So let me just insert another one. So this is IA. And this is positive sequence. I did not show the direction of rotation. Normally it's anti-clockwise. So that's IB, and that's IC. But as we are drawing the positive sequence, so we should show one here for each of them. You do it step by step manner. You don't worry about how we'll get it. So what is the relationship between the IB and IA? Because our reference is IA. Phase A is always the reference. So where it is now in terms of the angle from IA is 240 degree. So IB1 is A squared IA1. And you will see how I did it. Sorry. Can you see it? How I found the expression for IB1 for positive sequence from the positive sequence phasor diagram. Can you see it? If you forget, don't worry, you can go back here and get the value. So squared IO1, now what's the final answer? Anyone?
Sir, I'm getting 5.77 750 at an angle of minus 150 degrees.
Minus 150 degrees, yes. Or it can be plus 210 as well. Am I right? So IB1 we got it. Anyone to verify before we go to the next one? So I guess others also got this value. So now we need to go to the next one, IB2. IB2 is negative sequence current. We'll have to draw the negative sequence because we don't remember. But let's do this IC1 because IC1 is coming from positive sequence. So looking at the IC1 and IA1 is our reference phasor. So where it is at an angle 120 degree, and at an angle 120 degree means A only. So it is AIA1. Can you see again how the expression is derived from the phasor diagram for IC1? So you will let me know when you got.
Sir, I got 5.77 an angle of positive 90 degrees.
5.77 at 90 degree. That is correct. So you will let me know others if you are getting the same value or not. So okay, let's get that you are just copying and writing in your book, which is still okay, no problem. So now we need to find out IB2. For that we need to draw the negative sequence phasor diagram, and I'm converting it to negative sequence. So it will be IA2, IB2, IC2. But is that correct phasor diagram for negative sequence? The answer is no, because it's negative sequence, it will be swapped. After A, it will be C, I, C, B, A, C, B. So we changed their levelings. So now this is a correct negative sequence phasor diagram. Now we go back to C, IB2, where IB2 is located in reference to this phasor IA is 120 degree. So it's now AIA2. Not, sorry, oh goodness. AIA2. Always remember that 1 is related to 1, 2 is related to 2, 0 is related to 0. So AIA2 for IC2, it will be a squared IA2. So if I can just copy and change the notation, IA2 should be able to calculate these two values with no difficulties.
So for IB2, I'm getting 5.77 at an angle of 150 degrees.
Yes, that is correct. 5.77 at an angle of 150 degree. I'm not writing the ampere here. You must not make that mistake. It should be always there, because I'm writing that angle without that symbol of angle, which is normal, not a normal practice because of this PowerPoint. But at least we are managing to write those expressions as correct as we can. So make sure that you can calculate all these values. Even if you forget the formula for IB2, IC2, IB1, IC1, how can you get them from the very fundamental, from where you don't need to remember anything? Just basics will help.
So for IC2, I'm getting 5.77, but the angle is minus 90.
Minus 90 degree, it also can be positive. How many degrees if we convert it to positive? That's why that phasor diagram I was showing, the angle can be plus minus, or the magnitude can be turned to the opposite sign.
I think it's 270 degrees, so?
Yes, or plus. So sometimes we get confused with that, but if we know this, then we will never get confused, because you will go and tell someone that is minus 90 degree, then they would, okay, what is that minus 90? Then because they might not get it straight in the very beginning, but if you say no, it's 270, then they will also understand what you're saying. So now we see from this tutorial that when we did not know the value of the line current B, while the line C was open, only the current of line A was given, we were able to calculate the line current of B and utilize that to calculate the sequence component of currents for line A only, and then utilizing those we calculated for the other two lines, meaning B and C, and meaning all. Now we have all 9 values: IA0, IA1, IA2, IB0, IB1, IB2, IC0, IC1, IC2, and we don't need to worry if we have forgotten the formula for IB1, IB2, IC1, IC2. We always can go back to the phasor diagram, draw those respective sequence phasor diagrams, meaning for IB2 I have to draw the negative sequence diagram. For IB1 I have to draw the positive sequence phasor diagram, utilize that in terms of that complex number operator small a, and then we get it straight away. The calculations are easy. Either they will be related using a only or a squared, because the angles are either 120 degree or 240 degree. Is that clear to everyone?
Yes, sir.
That's good. Anyone has any question up to this point? Make sure these are very fundamental. The reason why I'm spending so much of time is that we cannot afford to make any mistake in this calculation, because these values will go in further and further and further, and at the moment you don't have idea, but you will see it in real life application. These values will be included in the calculation of protection, and those values calculated will go be inserted in the relay settings, protection settings, and because of that protection settings, things will happen. Either the protection will operate or the protection will not operate, meaning we're leaving things for to be destroyed or not. And when I'm saying things for destruction, is thousands of billions of rands. I'm not sure any one of you are following that news from ESCOM. How many billions? Did you read that news?
So there's always news.
Yeah, but I'm not talking about the news itself. I'm only talking about the how many billions. So it's responsibility. That's what my point is. So thank you very much. So do you need a break before I go to the next one? Do you need a break? 5 minutes, or should we continue? Tell me quickly.
I think we'll take the 5 minutes, sir.
Okay. Thank you very much. So let me prepare the next one. Another thing, just during this break, I want to let you know, I told about that in the email, that don't submit PDF file only for the assignments reports. Just submit Word file. Some of you submitted Word and PDF. You don't need to submit both. Actually, just the Word file is good enough. will come at 1040. Hello, please let me know if you are back.
I'm back, sir.
Okay, I guess everyone is back because I gave extra 2 minutes. So we need to draw the sequence networks. Now the tutorials are now being extended and extended coming to fault analysis, but not yet there. We're still in the middle. So we now need to draw the sequence network. We not only calculating sequence components currents and stopping there. We are going to the next step, drawing the sequence networks that will be utilized in the later stages to calculate the fault currents, sequence components of fault currents IA0, IA1, IA2 that we got from the voltages and currents in the other tutorials. So the power system diagram is shown here. What we have here, we have a generator. And we must observe this power system diagram that is given. If it is not given, the texts will be provided that will help us to draw this phasor diagram. Draw this system diagram or simple diagram representing the system. So what we have a generator G, and how the generator is connected. It's star connected, solidly grounded. We have to observe that very carefully. The generator is star connected, solidly grounded. Then we have a line connecting. We can ignore the impedance of the line or the reactance of the line. Nothing is mentioned here. And then we have a transformer. The transformer is delta connected on this side, and the other side has star connection, again solidly grounded. After that there is a line. Again the impedance of the reactance of the line can be ignored, and what is shown there, F means is a fault point, grounded. So what type of fault we don't need, because we just asked to draw the sequence network. And what else is provided? The sequence impedances of the generator and the transformer are given. Generator sequence reactance resistance is being ignored because we find that the reactance is much higher than the resistance, so ignore the resistance when we don't need them. So reactance, positive sequence reactance, negative sequence reactance, and zero sequence reactance for the generator. And for the transformer, if we remember that when we studied, we found that the transformer will have only one reactance, positive, negative, and zero sequence. They are same 0.05, 0.05, and 0.05 for X0 as well. So these are the data and the system that is given for the tutorial. We have to draw the sequence networks, means we have to draw positive sequence network, we have to draw negative sequence network, we have to draw zero sequence network. And for those three networks, positive sequence, negative sequence are much easier than zero sequence network. If you remember, for zero sequence network, we have to consider all those, what is if it's a generator or it's a transformer, and what type of connections are there, delta, star, grounded. We spend some time on that. So that is coming into this tutorial now. So the first one is the positive sequence network, and for that what we do, we need to draw it. I'm drawing it, although it's difficult to draw, but I'm doing it so that you understand how to draw and do it for yourself. So first of all, we have to draw a reference bus or neutral bus. If you remember, in power systems 1 we also did it, but it was only for one sequence, positive sequence. We did not need to know. So this is N1, the positive sequence reference bus or the neutral bus. You can show it horizontally, you can show it vertically, but as the system is shown horizontally, so I'm drawing it that way. It makes it easy for me, it makes it easy for you. So that's the first thing, neutral bus. After that we have a generator. So positive sequence diagram will have a generator to be shown. So I'm showing a line, but it doesn't have any impedance, it's just for connection. and then we'll show the generator. For the generator, there will be a voltage source coming into it, so that voltage source will show it like this. It does not necessarily need to be filled in, no fill. So that's the generator, and for that we will show a voltage corresponding to that, and the leveling should be done as well. So what we'll do, we'll say this voltage is E1 corresponding to generator 1. You could also say V1, doesn't matter. And that's that one. And we also need to show the polarity, which side is plus, which side is minus. So we'll write that negative. Here, this side is negative, and we will show the other side positive. Let me, after the generator there is a line, so let me just extend that one here, and then I can put this one, so that makes sense now. So we have shown the generator now with its voltage V1, because it's 1 is for positive sequence, not for one generator number 1. Is 1, E1, 1 in E, with E is representing the positive sequence. So the negative side, positive side are shown. We need to know that, so that we know the flow of current and its direction. So that's the line. I just extended it to make sure that that is the line there. Then what we have a transformer. So for positive sequence, it's simple and easy. Like I mentioned earlier, we have to show the reactance of the transformer. Sorry, before we go to the transformer, we have to show the reactance of the generator. So let me just take a freehand something. Yeah, so I'm showing the generator reactance. It's difficult to draw using mouse. So the xg1, so it's, I will say x1 of g. I will say this one, leveling is very important. I will say x1 of the generator G. The positive sequence reactance only will come into this diagram, because this is positive sequence network. And after that, what we need to do, we need to extend that line. Now we can go to the transformer. Transformer reactance is x1, positive sequence reactance only will come into this one. So we can copy this one and paste it here. So this one is to be now labeled. So it will be the positive sequence reactance of the transformer T. Make sure that you always follow the labels there. It was G, capital G, so that's why I put it capital G. It was T, so that's why I put capital T. 1, again x1 belongs to, sorry, corresponds to this x1 of transformer T. They are also shown as G and T there. So the transformer is shown. Now I need to extend this connection a little bit to reach the F, which is the fault point, and this has to be leveled again, and this leveling is not going to be F, it is going to be F1, because 1 has to be there. And normally we put, I normally put a dot there to indicate that the point, sorry, I normally put a dot there, because we will interconnect these sequence diagrams. So when we will have to interconnect them, what is happening? Shape field, hi. let me make it big first, then I normally, what is happening? Oh, I was checking on the so we can put black. Let's put black. So that's the fault point. Now I'll make it small. So that's the fault point F1. Now we must make sure that all the levelings are perfectly done. Started with the neutral bus of the reference bus, labeled as N1. Then we have to show the voltage source, which is E1 for positive sequence, corresponding to the generator that we have. And then showing the generator reactance. Positive sequence reactance will come only. Then we show that X1 of the generator G. Make sure that we put that G there, because this is the simplest one again to start. We'll have 2 or 3 generators in the following examples of tutorial. And then we show the transformer reactance. Again, only the positive sequence reactance comes in, and then we show the fault point. Now that's a diagram for positive sequence. We have done it. Now the next step is I extend this to calculate the equivalent reactance. From this, the next step will be calculating the final value, calculating the equivalent reactance. But again, this is positive sequence reactance. It doesn't have only one component. It has a generator, it has a transformer, it doesn't have any reactance from the transmission line, but we will have to go to this step before we can proceed to fault calculation. Although this is not asked in this tutorial, but I'm extending this. So calculating the equivalent reactance. So what are the reactances present here? Here, 2 of them, generator and the transformer, and they are connected in series. So the diagram actually be reduced. So what we'll be doing, reduced diagram. If you remember in power systems 1, we did the reduction like we do in control system. When you have a number of blocks connected in series, parallel, various combinations, you finally get into one transfer function, and then you, oh sorry, so what we going to do, we're going to reduce this one, the reference bus, and the voltage source will remain there, but we will end up having, oh sorry, why didn't I copy? And this one will be equivalent, X1 equivalent. So that's the X1 equivalent. So what is the X1 equivalent? You must let me know. It's not difficult. You don't even need a calculator. Tell me the value of X equivalent. We have X1 of generator is 0.2 and X1 of transformer is 0.05. So it should be 0.25 per unit. Is that clear? So that's the reduced diagram for positive sequence and the effective or equivalent positive reactance shown in the diagram. That is what we have to do in the first place for all of them. Is that clear? Please let me know so we can go to the negative sequence.
Yes, sir. Yes, sir.
Okay, that's good. So let me just copy these things. Okay, let me copy this whole thing. So now we coming to calculate. I kept this diagram so that we will need the values and looking at the system. So we calculating the negative sequence reactance and negative sequence network drawing. So for negative sequence network there should not be any voltage source, so we will not need them. We need to show the reference bus, which is N2 that we start with, and then what we have on the system, we need that. Look at the generator. So generator negative sequence reactance will come in X2 of G. After that we have the transformer, so X2 of T will come in, and then the fault point will be now labeled as F2. Please let me know if you understand that. It's simple and easy. If you don't understand, please let me know so that I can try to explain it again. You understand. So X2G for the generator, X2T for the transformer, and then the fault point F2 starting from the reference bus neutral must be shown as N2. So everything is 2 here shown, reduced value or equivalent reactance. There is no voltage source for negative sequence, so we must remember that. So what is the equivalent negative sequence reactance on the reduced diagram? What we have here, 0.15 and 0.05, they are connected in series, so it's 0.2. Is that correct?
Yes, sir. Yes, sir.
So everyone got how we drew the negative sequence network and then reduced it to get the equivalent negative sequence network, and the diagrams need to be shown in all the tests, examination and study, otherwise we will not understand. The marks will be deducted in the exams and tests. You must make sure that you always draw the diagram, show the proper leveling and things like that. Sorry about the reactance drawing. I could see how good I am in drawing these reactance. Oh goodness. So can we go to the zero sequence now?
Yes, sir. Yes, sir.
Okay, that's good. Let me copy this one again.
Sir, just
Yes.
to confirm, the negative sequence doesn't have a voltage source.
No, it doesn't have a voltage source. For voltage source only comes for positive sequence. Now we are going to zero sequence network. Voltage source comes only in positive sequence network. So zero sequence network, we must make sure that the neutral bus is N0. And what we have the X0 of G, and then we don't connect them like that initially. This is the complex one as compared to the positive and negative sequence networks. So what we do it in a step-by-step manner. The first one, we show the generator reactance, right? So after that, what we do, we leave a open there, and then we look at the connection of the generator. Like this is the opening I'm showing. Can you see the open here? Let me put these dots so that we can see them easily. that I'm leaving this open here for the generator type of connection is star connected and grounded solidly. So when star connected grounded solidly, what we know from 0 sequence component of current can flow in the lines. If it was not grounded, the 0 sequence component of current cannot flow in the line. So now we actually can close this open. We initially leave it open, but after looking at the connection and observing and applying those theory that we have learned, I put it in red so that we know that we started with open and then we closed it looking at star connected grounded solidly, so the 0 sequence component of current in the lines can flow. So that's why I closed it, because it can flow. If it cannot flow, we'll leave the open as it was. So the generator part is done. Is that clear to everyone?
Yes, sir.
Okay, so now we're coming to the transformer. We will start with 4 switches. If you remember that we have had 4 switches for generator, for transformer to draw the 0 sequence network. So we'll start with 4 switches, meaning 4 openings. So the first one is here, the series one, and let me draw this line to connect with this opening. So that's the first one. So that's the first series one. Let me we'll put them here. I can just probably go a little bit on the left hand side. Yes, so I can draw the other opening. It takes a little bit of time on the computer screen. I'm sorry. It was hand drawn on chalkboard. It would have been easy and faster as well. So that's the series. This is the first series opening for transformer, and this is the second opening for the transformer on the other side, high voltage or low voltage side. We don't know because it's not mentioned in the tutorial. So the series switches are drawn. Now we'll have to draw the parallel switches. So for that, what we do, we draw the parallel switches. If you don't remember, you just can go back to those previous slides from the PowerPoint in the notes. So we'll have to draw 2 more switches here, meaning we keep them open. And let's put this and then we'll have to copy these lines to what happened? So they are connected together. Now we have 4 switches for the transformer, and after the transformer, what we have the fault point. So now we can extend a little bit. Sorry, it's just pending. Word is not a good application for drawing, so but it's okay. We can show the fault point here as F2. So the drawing is done, but for the transformer, the connection type needs to be now configured together with the grounding or not. This has to be connected. Now looking at this side, what is this side in terms of connection is delta. So when it is delta, if we remember if the winding is connected in delta, we leave the shunt switch open. Sorry, if it is connected in delta, the shunt switch should be closed. The shunt switch should be closed. So what we do, we copy this line. So this is red now. can make it a little bit thick so that we remember. That we shorted because of delta connection. Shunt switch is closed. It's delta connected. It cannot be star connected, grounded at the same time. So we leave the series switch open as it is. So we're done with this side. So we can go to the next side, which is this side. Star connected, grounded. So the series switch should be closed. So that's the series switch. We close it and we are done with the diagram. But one thing I need to complete is that this connection needs to now go to the reference bus. So let me just label it at the top and extend it a little bit. This transformer connection needs to go to the neutral. Let me copy this one. This now needs to go to the neutral bus. That's what we did. So this is how we show the transformer connection. When we draw it, we leave the 4 open switches there, and in the middle we show the transformer reactance, and then connect it back to the neutral bus. So this is our complete connection now. Now if we want to reduce it to its simplest form, what we will have? We'll have the N0 and then X0 equivalent and the F0 as the fault point, and the value needs to be calculated. And can you tell me what is the equivalent reactance? And when we calculate the equivalent reactance, it is always, we must remember that it is always in between the neutral bus and the fault point. Equivalent reactance is in between the neutral bus and the fault point. So what is the equivalent reactance here between the neutral bus N0 and, sorry, this has to be F2. Sorry, this has to be F0, not F2. And also this has to be X0T, not X2T. Everything has to be corresponding to the sequence 0 0 2 2 1 1. Sorry, because I copied and pasted. That's the biggest problem with when we copy and paste. So what is the reactance now in between N0 and F0, the equivalent? Anyone? You start with the point F0 and try to reach N0. You start with F0 always and see how you can go by reducing and reach N0. So you start from F0 here. What you see, you can continue. Can you go this way? No, because there is open. So you cannot continue this way and reach the N0. So you cannot. So what you do, you try this path and then again you come here. Can you try this path? Yes, you can go. Then check the other part. Can you continue this way? No, you cannot, because there is an opening. So what you can find now or see that this is the only way you can reach from F0 to N0. This is the only way you can reach the neutral bus from the fault point, which is giving you only X0T, and hence X0T is actually the equivalent zero sequence reactance. X0T is 0.05. So the answer is 0.05. Do you understand that?
Yes, sir.
Everyone, I need to know from you all, because this is still very simple one. We'll have a lot of transformer, and again 2-3 transformers will be connected, different connection with grounding impedance in between, and also a tertiary winding transformer example is there. I want to do that. That's a very long one though. But is it clear to everyone starting from the drawing of positive sequence network showing N1, the voltage source, showing the polarity, negative, positive, showing the generator reactance, showing the transformer reactance, all the reactances, the way they are connected in the system must be shown. In this case, it's series, so we show them as series, showing the fault point, and then we reduce the diagram, and then we get the final equivalent reactance in its simple, but the voltage source still remain there because we cannot reduce it. We come to the negative sequence network, there is no voltage source present, should not be, only the neutral bus into the negative sequence reactances as they are connected in the system, either series, parallel, whatever combination is there will have to appear in that form here, and then we finally reach the fault point. When we are done, we reduce the diagram, get the equivalent reactance showing all the corresponding levelings into the reference bus, X2 equivalent, and then F2. So they are again connected in series. We look at that, so we get the final value of the equivalent reactance. We come to zero sequence reactance is different, a little bit difficult for us as compared to positive and negative sequence. We need to start with the reference bus as usual, N0, then we show the generator reactance. We leave it open because we need to look at the connection of the three-phase windings, is star connected, delta connected, grounded or not. So that switch was left open, and then we go back, look at the star connection, grounded solidly, and that allows zero sequence component of currents to flow in the lines. That's why we can close this one, the thick red line. After that, we draw the transformer like this. Let me put it in a circle so that we remember that this is the transformer portion. We always start with 4 switches, that including that line going there. Including that line connecting to the neutral bus, and then we look at the connection type, meaning is it star connected, delta connected, grounded, how it is grounded, all those. Then we close either of those 2 switches. Out of 4 switches, only 2 switches will be connected. So the first one is delta connected, so the shunt switch needs to be closed corresponding to that side. So this side is this side, so shunt switch is closed. If we are done, we go to the next side, star connected, grounded, that can allow zero sequence component of current in the line. So shunt series switch needs to be closed, thick line red, this one is left open. We reach the fault point, and then we can reduce the diagram, and when we reduce to find out the equivalent reactance for any sequence of network, we start with the F0, F1 or F2, meaning from the fault point we try to reach the neutral bus and find out the equivalent reactance. So in this case, we start with F0, we try to go this way, the line is closed so we can continue, but we can take this route, cannot continue because there is an opening. We can go to this line, and then we continue, we find that we can continue and reach the neutral bus, fine. Then we need to find out, is there any other way to continue and go reach the neutral bus. So we continue from here, we go try this way, we find that there is opening, cannot continue. Then finally we find that only one way of reaching the neutral bus is this way. So all these reactances present in this path will be coming into the calculation of equivalent reactance, and in this case only one reactance is present, and that is the reactance of the transformer, which is zero sequence reactance, X0 of the transformer 0.05, that comes here as the equivalent reactance. Is that clear now? I just repeated it for us to remember and understand it more clearly.
Sorry, sir. For the generator, it's in series because it's star connection and solidly grounded. Okay.
Okay, I just said, we'll come again with the question. If there is anything embedded inside, I am trying to find out that in your question.
No, sir, that red line by the generator.
The first one is for the generator, this one is for the generator.
And you put it there because the generator is connected.
Star connected and grounded.
Okay. So if it was like star connected, it would just be open.
Yes, of course. If it was delta connected, it will still be left open.
Okay, thank you, sir.
Is that clear to everyone? We are over time, but it's okay. We managed to complete this one because I extended that part to the reduction of the networks and getting the equivalent reactance for each of those sequence networks. So we are in the middle. Thank you very much. Keep well.